Yeah, click on that one. Open this way. Come on. All right. Okay, I'm going to start with sampling techniques because this is the big idea that has to do with reconnaissance, looking over. So sampling techniques can be used when we're just doing field walking and decide where we're going to walk, or perhaps do something that is not related necessarily to excavation, like some of these ground penetrating surveys. Sampling techniques are also used when we're making the decision of where to excavate and how much we'd like to excavate. So it works for everything in chapter 3. So let's just look at this first. So I wrote down test pits, but this can be also how to decide the best that you can on how to do some other basic identification techniques. So sampling techniques usually are put into place when we are first beginning the project. They come before a lot of the other activities, but they come after having an idea that there is an area that you want to investigate. So in your reading, it talks about using historic records or using ethnographic data, talking to the descendants of the individuals that might have used that zone. And then this might be your next step in the project. So certain research questions. Sampling techniques, if there's been an archaeological site, like the one that's in your reading in chapter 3, when they're talking about the archaeological site known as Teotihuacan, that's in central Mexico. Sampling techniques are not really necessary anymore because they've been working on the site literally now for about a century. So it's something that happens usually in the beginning, or if there's reason to think that that you've discovered some data that indicates that the extent is far bigger than you thought it might have been in the beginning. And that can happen too. So basic idea here, when it's not really clear on the surface what is beneath. So what the extent of it is, where the edges of it are, or what the internal components would be. So this is going to be on the surface. All right. I need to make some of my things go really tiny here so I can see. Okay, so here are a few things to remember as we get started thinking about this, and you've got breakout pages in chapter 3 as well on this. Just want to make it simpler and super accurate for the notes that you have as you get ready to answer questions. So we use sampling techniques to get a picture of an area, knowing that it almost never happens that we will excavate or locate everything that was left behind. There are a few historic places or very small circumstances where archaeologists are hoping to uncover all of it, the whole layout, all the levels, collect everything that they could have collected. But generally, we know that we're not going to do that. Second one here, why aren't we trying for everything? Well, a lot of times there is not going to be enough time to carefully excavate, survey, probe, or investigate what might be there. For instance, a lot of archaeology in the US today is started because construction projects are going on. So there's going to be road or drainage or a new building or a whole community, or we're going to use the area for something else. And so even if there is archaeology, they may only have a very brief time to excavate whatever they can, and then the rest of it will be trashed. Staffing, enough people to do this. So while there are a lot of people that would like to participate and volunteer, When it's really delicate, academic, and complicated archaeological survey or excavation, then the number of people that really have a lot of those skills goes down. And unless they're just taking part in a class, then they need to be paid. Right? Preservation. We know we're not going to find everything. That was one of our first concepts from the very beginning of the course in week 1 or 2, that most things are not going to be preserved. So we really know we're not getting a full picture of everything. And then funding. We talked about that last time too. The reality of archaeology is that this is quite expensive, and there are a whole lot of other things to take into consideration as we do our projects. So sampling techniques are a really practical solution for anyone who would like to, either professionally or as a nice sideline, or a lot of times people come into archaeology as retirees where they've always wanted to do it, but they had some other pressures or budget where they needed to stay in a certain area or those kind of things. So we do sampling techniques as a really practical solution, and use these 4 strategies in order to do the best that we can statistically for a reasonable representation of the area. That when we do those samples, that there's going to be a pretty good look at distribution, depth, nature, and variety of what might be there. Right, so those are the limitations and needs. So let's look at a few. Okay, so sampling strategies are used for both field survey and excavation. They are used for both of those stages when we're just either field walking. We looked at that in a couple of different areas here where people are just out looking down at the ground. And then also if they're making some decision of where to excavate. So again, in both of these cases, the main thing going on is when you know that you can't see too much on the surface and that what's beneath is not going to be really, really clear. So the type of sampling strategies, and we'll break these out and look at them a little more, go from everything from completely random, and that's what this one is here, where they just have already made a map of the site. There's already a datum, and then all of the territory has already been mapped and put onto a grid, the same thing we would do for a neighborhood or some sort of construction project. And then they use a computer program and tell it to divide that grid into whatever measurement strategy they want to. It's going to be in meters, but it can be every 10 meters, it could be 6, it could be more. And then they just ask a computer program to randomly generate locations on that grid. And so you can see, while some areas didn't get any generated, others randomly got some that were side by side, where you see some of these, they're a little bit bigger. So this is before they've done anything. This is just where they're going to either do a test probe, a small test pit, or one of these other sampling strategies. If it is more of a systematic one, then in that case, they're really breaking it down, and you can see that there's going to be a sort of a regular pattern for those. So let's go ahead and look at these individually. There's 4 of them. All right, before we enumerate the 4, a couple more reasons why, even if we did have staffing, or even if we did have a little bit more funding, that we don't necessarily want to dig everything up. Mentioned this last time too, but no harm in an intro course in doing a little bit of repetition, because then when you see questions to answer, they'll be more clear. So in the interest of best practices, we really would like to leave some areas covered up and untouched. If it isn't being excavated because there's going to be a ruination of the site, right? If it's in fields or a natural area or in a valley system or somewhere in the coastline where people aren't living, then we can leave part of it there because excavation is destructive. So we may have really good reason, and in this case, scientifically verified reasons, to know that in the future, sometimes not all that far away, there may be really better techniques or technologies invented to help us analyze or manage or preserve what it is that we're locating. So leaving areas untouched leaves them ready for improvements in the field. And of course, especially when we're training our students and ourselves, we're already doing this, to be thinking constantly about scientific ramifications, about all of the aspects that we might want the data for, and thinking about retraining or training new generations to use new techniques, new invented strategies, new technologies as they are coming up, then there's good reasons to leave certain things untouched. A good example of this would be the world's biggest known ancient burial monument or cemetery monument is in China, and it's called Mount Li, like mountain, MT, and then Li, Li. Mount Li is incredibly important. There's historic records. They have a good idea of the basics of it, and they are not interested in excavating it right now. It's so important. It's so enormous. And when they break into it, things are going to start to decompose because it was an entire wooden structure and incredible other things that were placed inside of it. So right now, no purpose to damage that or ruin or lose some of the data at the moment. So they haven't started doing that. They've been working around it and with incredible results, but they are leaving the most valuable, the most delicate thing for some other time. And extremely expensive, extremely slow, a huge number of people would be working on it. So here they are, just the titles before we start with a little sketch. Simple random, stratified random, systematic sampling, and stratified unaligned systematic sampling. I know the titles are pretty similar, so that's why I wanted to break this one out, not just leave it for you to work on just in the textbook alone, especially since it may not be the most exciting thing that we look at, but for doing archaeology, it's a very core technique. So simple random, stratified random, systematic, and stratified unaligned. Step over here for a moment. Okay. One of my things giving me a chime. My house has some stuff later on today. I have to have somebody come over and tell me what needs to get fixed and about how much it's going to cost. And it's going to be pricey, I'm pretty sure. My house is almost 100, so it's not unimaginable. All right, here we go. Simple random. So a little sketch right here on the side. You can see that the whole site has been mapped out, and they're just putting it in a square, and they put these little hatch marks on the edges. So they decided to do this in 1, 2, 3, 4, 5. 1, 2, 3, 4. So in 20 basic squares that would come through here, and then the little black boxes, a computer program randomly stuck them in there in a random pattern. So simple random is just looking to understand the site as a whole, not areas where somebody walking on the surface found something and they're very interested in digging right in that spot to see what else is below it. So they use a table of random numbers, generated by a simple computer program. Not simple for me, but for people that do this, simple. The archaeologists get help from the tech folks. So the computer runs out and tells you the addresses of where within that zone that the samples are going to be taken, not a person, because even though people sometimes say that they're not biased, the truth is, and I know lots of you have already learned this in other courses too, there isn't any way for a human being to not be biased. Even our ability to notice things in nature is built in to things that happen as we're growing up, to our own experiences and so forth. That's why it's so important in archaeology to have folks from different generations, different genders, different educational backgrounds, different cultural backgrounds, different belief systems to work on these things. They will, to a certain extent, notice certain things in common, but there will be other questions or other ideas or other possible solutions that will occur to some individuals and not to others. So the sampling areas then define where you're going to be, right? You start out with a map of the whole site. It's got a datum or a 0 point, and that's how we are able to label all the things that we find and say it's from this particular part of the grid or this square or this unit. And then the machine says, what is this, sample units? You type in how many units you want to put in, and then how much of the area you want to sample. So this is just randomly spit out by a computer after you put down some parameters. And again, some of these are going to, in many cases, not find anything culturally related. Others might be surprisingly where you thought it wouldn't be something that was culturally related, and you find things as a surprise. So you get surprises on both ends. All right, that's simple random. The more you sample, the more accurate your results will be. But if you don't have much time and you don't have much money, then you can only do what you can do. All right, stratified random. Now stratified is the key change right here. And you can see on this one, there's this dotted line, this hatched area over here, and another one. So again, this box just indicates that the site has been mapped on a grid, just the same way we would map anything in nature. Now, in stratified, they divide up the region by natural zones. So if there's forest zone or a riverbank or a pond, hillside, a rocky outcrop, or if there's something that, if the site's not too old and we know there's a farming area there and we know that farm goes back a long period of time, you divide those up into several separate zones. And then the sampling squares are chosen the same way that we just talked about with simple random, but you make the machine be sure to assign a percentage that fits the percentage of the environment. So like this one, if half of your sample was a forested area, then you tell the computer program that's going to pick the random locations to pick 50% of the samples in that region. It's so that you don't leave out something that's key to understanding what's going on. So especially if it's a hillside or the top of a hill versus the bottom of the valley, or where you've got ecological or environmental zones where people might have been using them differently and we don't know exactly what their favorite or their choices might be. So it's called stratified then. And then this one's divided into the natural zones and then the percent. So this one looks like it's 2/3, let's say, or 3/4. So the machine would say in this region here, in these particular grid, randomly pick 65% of the squares. In this one, randomly pick only 30% of the total squares for the activity. No, that's not how that one works. systematic. Well, systematic's easy to chart out, right? So in this one, everything's mapped to, then the grid or a map of equally spaced locations. And then you just decide, are you going to do every other square, every 2 square, simplest one to plan and execute. Some of the pictures we saw of late 1800s, early 1900s excavation with some of those founders of scientific technology, because that's before computers, really did systematic sampling fairly commonly. So they would do this and leave the walls, the bulks or the grids up, and you can see that overlaying, and then they would just dig down to where they started to find the archaeological remains. So that one's pretty simple. The strength is, and the weakness is, it's a regular pattern. So you're not using any, you're not eliminating anything because an archaeologist didn't think anything would be found there. So you're eliminating personal bias out of it. But in this one, with regular spacing, if let's say, for instance, you are sampling in these boxes, but the street in this particular location goes straight down this way, you could miss it entirely and have no idea it was there. I might have mentioned a couple of weeks back, I worked on a project where they did that. We did 100 meters long on this systematic sampling grid, and we missed every single building and the whole downtown of this mining town. It wasn't until the town itself moved and had sort of a bend in the end of the road that somebody way up on this end who was doing a grid, let's say right up here, actually found something. So we had over 100 people that really didn't find anything except for an occasional nail or a little tiny bit of broken something because it was in the middle of the street. So you can miss everything. So that would be a weakness of systematic sampling. Alrighty, we'll move forward because you could take a look at this again, and your textbook does talk about it a little bit too. And the last one, stratified, unaligned, systematic. In this one, they try to use all 3 of those concepts. So lay out your grid, right? You do the map for the whole site, got a datum point, artificially lay that grid over everything, then put the computer model within that grid. You've got your standard sections, you're orienting everything, and then you decide how big you want your sampling areas to be. And then within those sampling areas, you randomly choose a zone within it. So if this is this square, this is this square, this is this square, this is this square, then it was random whether it was up in this zone, somewhere closer to the middle, the bottom corner, closer to the upper middle center, and so forth. This one, very popular because there's probably no bias in the sampling at all. And it does make sure that you've got really evenly spaced prospecting or reconnaissance. Okay, then I can tell you're super excited. So let's get out of this one. And stop share for a minute for that one. Okay, so this is when it talks about in the rest of the areas of your reading or the next couple of lessons, lesson segments, I'm going to break them down into smaller sections for you. Then when they're saying, when you're deciding where to do this, that is the basis where the deciding where to do it, when you're getting ready to start the project. So let's go over to a new section of it then. And we're going to take a look at locating. Okay, so what I did with these, I have 3 little sections here for you, is to just give them the basic same heading as you had with your reading, where it said that in chapter 3, you have a section where they're talking about locating things, a section where they're talking about the layout of things, and then the 3rd section where they're talking about excavation and strategies. So let's do this first part of it. So again, reconnaissance starts first, right? And we talked about whether it's going to be simple random, the SUSS one, stratified, etc., or systematic. So they're going to, after you've picked one of those 4, and now we'll see what kinds of techniques can be used. All right. So we're not going to try to learn, yay, in our class, every single type of technique that we can bring to bear. I want to focus on a couple of them. And you've got some case studies in your reading that focus on these as well, or not in your reading. There is a case study in your reading, but in Canvas too. And so those will mention as we go through this one. So reconnaissance again, taking a look and trying to figure out where things are, especially if it isn't really obvious while you're on foot or looking around with just your own human eyes. So we'll look at a little bit for ground survey, which we did just now, aerial or GIS. Okay, so basically when you're reading this or these types of terms, how do we find, map, and figure out where sites are located, and how, using these first parts, can we figure out the overall size of the area, the layout of the area, where there might be more concentration of things, where you might be on the edges, and possible functions. So we can start some of that by starting right on the ground. And your reading talks about using documents like cultural resources and then the survey strategies. And we just did that. Take a look. Now those same patterns for survey strategies work whether you're doing them on foot or whether you're going to excavate in that survey strategy. Both of those use that same 4 basic ideas there. Some projects, especially if they've been going a long time, don't have to do the randomness anymore. But right when you're beginning out, usually the random ones are used. And then the other grouping there, so we've got ground, that's why it's in blue. Then aerial techniques, we talked about, there's a few mentioned in your reading. We're going to just look real quickly at photography, aerial photography, an aerial process called SLAR or SLAR, and an aerial process called LIDAR. And then, not today here in the presentation, but in Canvas, you have a little bit of video talking about satellite aerial reconnaissance. And then there's geographic information systems. So I don't have a slide on this because your textbook talks about GIS and the Giza Plateau, which is Egypt, one of the most heavily interested areas with tons of amazing architecture, burials, and other types of features there. Okay, so 3 types: ground reconnaissance, aerial reconnaissance, and geographic information systems reconnaissance. So let's go straight over to aerial, because we did survey strategies, and we earlier in the course talked a little bit about field walking, like last Thursday we did it, and it's a little bit in the first one. So let's talk about photography for a moment. Aerial photography, in other words, planes flying over the landscape, really got started not just for archaeology, but a lot of other purposes in around the 1910s. I think it's like 1913, 1912. And the photographs started to become detailed enough so that then when they were processed, people later on could start to figure out what was on the landscape. Two basic strategies for these: oblique aerial photography versus vertical aerial photography. And this is still widely used even today when we're trying to look at areas where either it's not accessible for us to go to or safe for us to go to. And again, archaeologically, for this particular, where we can't get there on foot or it's not safe. For instance, war zones or areas where people from different nationalities are not welcome. Places where the weather is not make it possible to go there at all, or the landscape, or something else that is just going to make it just dangerous or unwelcoming. So still really, really used. So what would be a good example of aerial photography still playing a role in archaeology? Right now in the Middle East, archaeology looking at the Fertile Crescent and what we call Mesopotamia is just not doable. Just not doable. Too many political things, too many cultural things, too many other kinds of issues. However, there have been a huge amount of data of really incredibly detailed aerial photography. So it is possible to make some analysis from looking at those aerial photographer. And so there are still some people publishing some information about distribution of things, at least if they're sort of being able to see them on the surface. Okay, so this is like the photo you have in your textbook. We can look at it here. You will see some images in quiz and exam for this unit and for the units coming up later. So just want to make sure you see it, because I know I'm going to use it for some questions. It just won't say that, right? You'll just see a picture like this with an arrow, just won't say what it is. So vertical photography, right, straight down. And this is really great for mapping and planning. So this one is going to be a good one to just go over and see kind of what's there straight down. So oblique photography is when you're doing it from the side, and the shadows there give you a better idea about topography, the up and downs or the rolling and subsiding of the landscape. But oblique photography is more difficult to analyze or interpret. And in order to really use this one, oblique photography, you've got to go there on foot to really double check and see what you saw and see if you were correct or whether there's something else that might have been confusing about it. Okay, so aerial, vertical versus oblique. Now, remote sensing. Two types of remote sensing are going to be important for us this semester, and they're developing some other techniques all the time, but let's just look at the two that have been used the most. SLAR, or SLAR, Sideways Looking Airborne Radar. In Canvas, you have a case study. It's titled Maya Wetlands. It'll be in the PDF case studies area from that one. So you do want to read over that and see where were they working, how old is the area, and what were they trying to document. Where were they looking, how old, and what were they trying to document, and how successful was it? What did they discover? So in this one, in Sideways Looking Airborne Radar, they're recording radar images of sending out a pulse and when that pulse returns. So it's based on electromagnetic radiation that they send out from the plane, and then they register to see when that hits something and comes back. So in the sequence of it, they can tell if something is taller or something is closer. And so you'll get, then you need a very fancy computer program to help you analyze that. So that's SLAR. LiDAR is the most fantastic right now and gets the most media attention. So LiDAR means light detection and ranging. It's also nowadays known as ALS, or ALS, Airborne Laser Scanning. So some of your questions, you all, will just be, what do these stand for? What do they mean? Well, just what's the definition of it? And the other might be, in regard to this, what case study you looked at that was illustrating that technique? And when do we use that? So
Dr. Brown, I have a question.
Yes, go ahead.
Just to clarify, you said that LIDAR and ALS are the same thing?
Yeah, for whatever reason, for the people that really do the electronic tech of it, it's pretty much the same thing when they're just, instead of calling it light detection and ranging, now they want to call it airborne laser scanning. You know how we are. We like changing the names of stuff. Yeah, so they'll be equivalent for us. In Canvas, you have a little case study there that's called the classic Maya lowlands, where they're talking about this. In that one, it's got its own page, and I just found an incredibly interesting, well illustrated web page, and just went ahead, and instead of you having to go to the web page, I just formatted it all up and cut and pasted it and put in Canvas for you. And they'll talk about what we can discover using LIDAR for that particular area. So in this case, they're using a form of radar that's based on infrared photographic film. So they do work somewhat differently, and they will give you a slightly different with details, but this one over here, LIDAR, is the one that's really, really turning things around for certain types of environments on the planet. All right, so in many cases, archaeological sites have things that are there, but they're underneath the soil, or they're underneath vegetation. So for certain environments, when I just say manually mapping, right, going in there on foot with our type of transit situations that we do, like the same that you see the road crews in your neighborhood who are doing some survey and trying to figure out where the underwater lines are, or gas and electric, or sewage pipes, or whatever it is, exact same kind of thing, and they're doing up and downs for it. There's just places where that just barely works. You can't get far enough away from each other, or the landscape is too dicey, or it just isn't as detailed as we'd like it to be. So, or it's an unhealthy environment. That would be another one. So light detection and ranging, or LIDAR, produces three-dimensional maps of the surface, and it's much, much faster. So a couple decades ago, up until a couple decades ago, in order to map things, let's say in the rainforest, you had to send crews of people out there every single day for not just months, but over years. And then by hand, put all the data in and try to start mapping things out. And it just was super slow, super time consuming, and not quite as accurate. In this one, it's really, really fast. So it kind of works like scanning something on a table scanner, but it operates from a plane, and the laser beams get directed to the ground. And as the pulses come back up, it's connected to a GPS system and a measurement system for the speed of it. And it will give you what they call a point cloud image over the ground. But here's the biggie. Biggest advantage, and the places in the world where it's changed everything, is that it can see really well through vegetation. So places that are covered in forest, big trees, small trees, incredible amount of plants on the ground, like swampy areas. So it doesn't have to be tropical rainforest. It can be swamp. It can be giant grasslands, even though there aren't many trees there, and so forth. So in places where walking. Yeah. So one minus, it's expensive, so you can't always really use it every place that you would like to. But eventually, over time, a lot of these are going to rate, the price of them will probably go down, hopefully. So Here's an example of one where you can see there's not a tremendous amount of forest that's here. Some of this is trees, but a lot of it is lower shrubs. And while the archaeologists and tourists, this is Angkor Wat in Southeast Asia, one of my bucket list places to visit once I have time and a budget and right, and don't have to worry about spreading super dangerous diseases, that I'd like to go. So this is a tropical area. Angkor Wat itself is gargantuan, but if you see from just so this would be a vertical photo, aerial photo. You can see that they've already done some excavation around this main building right here, and that there was a walkway out the front, and this empty area that was probably a moat-like area and still has water in it. But look at how dense all of the construction was all around it. And you can see none of this. From flying over it and from what people have been told and have thought about this is that these were just giant temples that were isolated from everyone, surrounded by water, and they just stood in the middle of the forest. This is why they always, for public media and for tourism stuff, say, oh, and it was so mysterious of what was going on. But look, this is a huge amount of really tightly built construction. And some of it are clearly in these sort of maze-like walkways. Now, whether this is growing something or housing something, or whether this is a meditation space, they would have to excavate to find that out. But there is far more here than could be looked over. Now, some of these, again, when you're looking at it this way too, from this, some of these little dips here may have been, and some of this, I think, to me is looking like they have done some excavation already in, right in the really regular grid type pattern here, systematic one for this, but yeah, completely densely covered in the history of the past in this area of the world. So the one that you're looking at though in Canvas is from the Americas, from the rainforest here in the area that's called Mesoamerica. So in the rainforest called the Petén, P-E-T-E-N. Now, this is actually just a photo I took at a traveling exhibit here at a museum here in San Diego, where they were emphasizing that LiDAR then produces a model or map that is topographic. In other words, it shows you the up and downs of what's happening as the pulses are directed at the ground, and then they're reading how fast they come back up. So it's machinery is mounted the airplane's wing, and sometimes you'll see this with lowercase I because the LI refers to one word, light, there. And then the recorder, our computer on board, is going to record the sequence of the bounce back from it. So anything that is harder than the leaves is going to bounce back at a different scan. So what the computer that reads that does is allows it to transform that scan into a nice map like we just saw with the other one. So then way more clearly we can identify what's actually there. Mounds, ancient constructions like roads, buildings, open space, those kinds of things. But as they emphasize here, you still have to go out there and take a look. But now you have a map and you know with GPS exactly where to go to take a look. You're just going to find out whether is that just a pile of rocks or is that actually constructed structure? Is that just an area that got flattened out in some other natural purpose, or is that a roadbed? Okay, so for the fun details of this one, you're going to find that in Canvas. There'll be a couple of things to take a look there. And it's a little bit longer article, but super fascinating. And it'll just show you somebody who went on a visit, an archaeologist that went on a visit to the region and looked around. Now, there's a link inside when you get to that page that takes you over to a quick video, because they wouldn't allow me to copy the video and put it into Canvas. Canvas wouldn't let me do that. So you just quick link out. It's only a few minutes long, and where they really talk about how much impact that has. So while this is how we do it, what we really want in our classes is to find out, what more do we find out? What really is the change? Or is it all just practical, like it's faster and we don't need to have people down on the ground doing it? Or is it resulting in some new avenues for discovery and analysis? Okay. All right. So let's go to my call out for the last one for today. And back to share screen. This one will be for not just aerial, but other types of determining the layout of sites. Come on. All right. So again, a little bit more with this. So this we did, again, surface survey. You've taken a look at that. We looked at the potential survey patterns. So now we want to look at subsurface question. What are, and for this one, what are a couple of the most commonly used subsurface investigation procedures, like this individual here in this photo from Mexico in 2017. Here, this site is very commonly visited by tourism. It's a major tourist draw. It's a site called Monte Alban. It's right near the capital of the state of Oaxaca, when the capital is called Oaxaca too. So for here, and so it shows him using one of these systems. And you can see he's walking out in this open area. He's got the grid laid out so he knows where he's gonna walk. And so they can keep track of exactly, and he stays on the straight line in his grid for this one. And then they're gonna collect that data and use it for some other things there. You know what, I need to stop this one for a second. I need to double check something. Just go back into it in a second. All right. Okay, now, not just aerial photography or aerial tech stuff like SLAR, LiDAR, or the other term for it, but they can use some other geophysical prospecting to do that. We're just going to concentrate on two, magnetometers and ground penetrating radar, or GPR. This is rapidly becoming one of the main standards in the field, but magnetometers for a while, and still one of the basic skills that anybody that's going to do very much field archaeology needs to learn how to do. So even if your textbook is going into more of these that are technically complex, you're going to see really, other than maybe just the name of something else, only to ask a little bit more details on just these two techniques, because they're the most commonly used. Okay, magnetometers. Up here on the right is an image of what you get when you're using a magnetometer to generate an image. And what you can see is in this particular area where it went over the scan, that you get these little hot spots, and it isn't actually heat. You get these little highlighted areas that are also going to indicate about where something that you might want to come back and take a look at. That there's something under there that's giving you a different value or is registering differently. And then as part of, right, and again, you always start out with mapping the whole site. You have to map it first. Otherwise, you'll never be able to find where these are later on. That's why I showed you the picture of the young man walking along on the grid and staying on the lines and having those little posts out there. Okay, so a magnetometer is considered a passive sensor. And what it is, it's measuring strength and sometimes direction, but the strength of a magnetic field. So by detecting any irregularities, anything that's popping up as different than what's around it, then it can indicate the location of items that in college speak are described as made of ferrous material, F-E-R-R-O-U-S. And you all, just in case, it's always good not to assume everybody knows every single term. Ferrous means chiefly metals containing or consisting of iron. So magnetometers are used a lot in certain kinds or areas of archaeological investigation. So when we're looking things that have a written history significance here, let's say in the US, where we know that they're using horseshoes and nails and some metal strapping to hold carts together or buildings together or structures or mining equipment or anything like that. Anything that's going to be for gutters or drainage. There's a ton more of the others. Then that's something that's going to be able to give us a better idea of where some of those things might be. If the buildings are all rotted away, let's say it's that mining town that I did a little project in. If the buildings are rotted away, back in the time that place was all built, the buildings all had metal nails, and all those buildings had cellars. And those cellars would have places where things had dropped down or collapsed as the building collapsed. And you would get, so if we had used a magnetometer, we'd get an area where there were lots of these little pingbacks or reeds of a concentration of things made out of iron. Magnetometers can be used underwater. I don't need you to go into a lot of detail on this, just that while it is a slightly different type of machine, it's got the same basic function or purpose. And of course, this is usually when the main thing they're looking for are sunken ships. So archaeologists are going to use a magnetometer to measure any type of human activity that would have increased magnetism in the area, where we might be able to get a read. So, for instance, now, if you are heating up soils and that sort of thing, depending on the geology of the region, old fire pits might have higher magnetic readings. Bricks, storage pits, and even sometimes old trenches. And again, we don't have to become experts on this, just know more or less what that kind of reading is used for, whether we use it all the time, what are its minuses, and what does the readout generally look like. So they do a good job of finding where those are, but they don't give you accurate depth information, like the next one we'll look at. So in this, they got a ping, but they don't know if this is 50 feet below the surface or 15 inches below the surface. They just know that they got a ping of something denser with more of a metallic read to it. Let me go back. So they find them, right? So this is location, but it isn't 3D location. That might be another way to think about it. So, super important part of the archaeology toolkit for decades, at least since the 1970s, and I'm not sure how much earlier than that. So there's lots of different types of machines that do this work, but usually you're going to see somebody, if it's a magnetometer, carrying something along with them that looks a little bit like sort of a cage to it, or with some straps. Sometimes if the ground is pretty, flat and dry, and there's not too much vegetation. They can have wheels on them. You can see that they've got the little computer that's doing the recording, and then the sensor that's going down. This is just along with these for somebody that found something. You can see them walking along with this one as well. So you don't have to be super strong. You do have to be able to go outside and be out there for a while, and you have to have it lined out. See, on this one towards the left, you can see the line, and he is walking directly over that line without mapping the site first and putting these grid lines out. Then you'll have a map that says there's something in there, but you won't be able to find it later. And it's a key basic skill for archaeologists today. So for instance, here's some students and workers with the equipment. They're carrying some of it, and they're headed out to do some magnetometer investigation here. But this is just an advertisement from just this month, a couple weeks ago, from the Society for American Archaeology, for people that were kind of local to where this was going to actually happen. So a 2-hour training so that you could get a certification that ups your ability to be hired for contract archaeology for there. And if you're a member, not very expensive, and really not super expensive if you're not a member. So, and then you could get a whole group of students signing up for these. These fill up really fast. By the time that I even found this a couple weeks ago, the class had already filled and run, but they run these all the time. So this is a real basic. So another thing to remember about it, a really basic skill for people working in archaeology here in the US. I didn't do much archaeology here in the US. Most of mine was out of the US, and we didn't have any of this equipment available. So I didn't ever learn how to do a magnetometer, but someday I'd like to learn how to run one. I had to do some survey stuff. You know what, that's an interesting question, and I don't know that. I do know that the companies that make these things make them, remake them, and so forth. So it may be that you have to get at least retrained, but I don't know that you would have to be totally recertified for it. But learning how to learning how to use the computer programs that go with them and do the analysis, we just have to redo. But I haven't heard of anybody's certification expiring so that you have to go out and get retrained for something. So yeah, that was 4 sentences of me saying, not exactly sure. I could look it up though. All right, let's look to the next technique. So here's a little video here. This should run, hopefully. Tell me if you can hear it. I think I set it up so that you can, but it's just a couple minutes. They're going to talk about, this one's good. It's here in the US. It's over close to the modern day city of St. Louis. And they're going to show you some equipment for excavating that's also in the end of the chapter. And then they're going to show you a little of this remote sensing.
I am standing in the remnants of a prehistoric structure basin, and what that means is they would have dug their houses semi-subterranean down into the ground slightly. So you can see here a line, hopefully, cornering here and straightening out here, separating this lighter, sterile subsoil that's undisturbed versus this dark soil that has bits of charcoal and burned clay and artifacts. So this is the type of anomaly that we saw across the area where we did magnetometry, several structures. We were targeting this specific structure because of its size and shape. We hypothesized that it may be a later Mississippian structure. We wanted to get an idea of what type of prehistoric disturbances and archaeological features were in this particular tract of land, because they are adjacent to these 2 borrow pits and we're so close to downtown Cahokia. So then the first step in doing that,
sorry about that,
was to set out our grid, which was an arbitrary grid.
Not not sure why it's
30 by 30 meter squares, which then wearing the machine that has 2 sensors, it looks like a football goalpost. The settings that we use, we have it take readings 8 per second, and I walk at about a meter per second pace on 1 meter transects throughout this 30 by 30 meter grid. And then there's a certain software that we use to then process that data to get it off of the machine, and that will show us in sort of a grayscale is what we use normally. Being a really positive anomaly shows up as a dark black or gray. A negative anomaly shows up as lighter gray or white, and those both tell us about that particular area of soil had been disturbed prehistorically or had been altered by thermal alteration. So something had been heated or burned there.
So you're basically looking for places where people pooped or put things on fire?
Yes, not necessarily poop, so any sort of organics just from trash, from food, from disturbing the soil, anything like that would change the magnetism.
Well, you actually can get them from your local hardware shop. So you get the steel blade shovels, and they have they come like in a point. And
I'm sorry, keep going.
you either buy or rent an angle grinder, and you cut the pointed part off. So you create this nice flat, even surface, and then you sharpen them on a bench grinder so that they are sharp on the back side. So we have a technique called shovel scraping, where you basically bend over and use your lower body to scrape the soil really nice and flat. And so this sharp end it slices through this really tough clay, and it leaves it in a nice flat surface. Trowel is the same thing, and it's also, wooden handle, which I prefer, and you sharpen it on both sides so it's nice and sharp, and you can cut string with it, and you get nice profile cuts with it, and it's kind of a mark of a good archaeologist. They have a nice sharp trowel. So it's a fun thing to tease students about when they don't have one.
All right. So they did show you a couple of the basic types of equipment: the shovels, the awls, the picks, the trowels, especially trowels. Really, really basic stuff. The only thing different about them is that we have to go ahead and sharpen the edges so that we can use them for our particular purposes. Okay, GPR, that'll be our last one for today. So geophysical survey is the general term, and geophysical survey has a number of other techniques, but we're just going to really look at GPR for the most part. So geophysical survey are, again, another fantastic way to identify places to excavate. And this one is really the one that's taking off a huge different types of or varieties of equipment that are being made. You'll see lots of companies doing lots of advertising for these, not just for archaeology, but for other kinds of purposes too. So GPR, ground penetrating radar. This one gives depth information. So while magnetometers told them where to look, GPR not only says something's here, but how far below the surface it is. So that makes it even more useful. It can sense up to 30 meters right now, and maybe they'll get better, 30 meters below the surface. So that's in US anomaly measurements, about 100 feet. So GPR and the other geophysical technologies are not usually used as our first phase of doing things. The equipment can be pricey, and running it and so forth. So first phase stuff, field walking, that surface survey that we do, that we talked about it, where people are just walking over the surface, looking to see, can you see anything there, and then coming back along. In geophysical survey, once you have an area that you are interested in where there seems to be something going on, usually that's when they'll either rent or access this particular type of equipment and the people that can use it. So usually after maybe you're doing some shovel testing or you've cleared the surface of maybe some of the vegetation or just the soft soil that's over the top, and you find something that points towards something more interesting. So they can use GPR also, especially in places where lots of things are still going on in the area. So maybe it's an agricultural and they've plowed or run something over the surface, and now you're seeing artifacts on the right up on the surface. Or a lot of times GPR can help us refine what's going on when we have a very detailed historical map that suggests what structure or structures used to be at the site. Okay, keep going because we got a few minutes left. So a GPR scan is going to look completely different than the magnetometer one. Remember, the magnetometer was looking vertically straight down, didn't show depth, and it was just showing where you got a ping. Now on this one, this is two-dimensional, and this is again going to, so this one also says what the system is, and I got this from a company that was trying to advertise things. So in this particular case, what it's showing here along with the measurements is when they started to find some of these subsurface disturbances. And what this is indicating here, see these sort of areas where things are not, it's just disturbed here. There's about a half a dozen of them here. This has actually ended up being an area where there were about half a dozen burials. And the wavy looking look to it would be about how many nanoseconds it took to get the differential ping. I'm just gonna say ping from what was going on. So GPR scans look different than magnetometer scans. So what happens? It sends a little pulse of energy into the material, right into the soil or below the ground. And then the integrated computer, and you saw the people, or we'll look at a couple pictures here, they carry the little computer recording box with them. It's not very big, and it just records strength and time for the return of anything that comes back. So anything below the surface that pings it at a different strength and timing is going to be picked up as an anomaly or something that is different. GPR works best in dry soils that are sandier, especially if they don't have much salt. But it is currently considered our most accurate, highest resolution geophysical technology. Where does it not work particularly well? It doesn't work super close to coasts where there's salt water, or sometimes some of those inland areas that are these salted seas, right, the Dead Sea and so forth. Too much high salt content, really not going to get a lot of details. You can get also salt in freshwater kinds of areas because the soil has salts that have gotten melted into the liquids are there. Dense clay-based soils can work sort of, but they're difficult to penetrate. It can't see through metal, so if there's a metal plate or something going on, it just goes through there and stops, and it cannot identify bone. So what they're looking for in that one where they said they were trying to look for a cemetery or burials is they're looking for the disturbance of the soil perimeter that they dug in order to lay the body down. In some cultures that might be a long rectangle. In others it's going to be circular because they bury their dead seated and they go straight down into the ground with their head up and their knees bent up towards the chest. So it doesn't work everywhere, but when it works, it really does a great job. So how important is GPR today? This is Scott Hammerstedt, and he is just a couple years later, he's the same person that we saw using the magnetometer in the first picture in Mexico. In this particular case, he is been working in Tulsa, Oklahoma, in order to try to help the community and the whole United States to identify and rectify the aftermath of the Tulsa massacre, where the town went into a very nucleated, highly functional, very, very healthy, business healthy, family healthy part of town that had mostly Black residents or entirely Black residents, and on a mocked up excuse, went ahead and burnt the whole thing down and murdered a ton of people. The bodies were just dumped someplace, and there's been many decades of nasty racism going on, and it really hasn't been until very, very recently that even the city of Tulsa has done much to attempt to actually locate where those people were dumped, so that the family's great, because the descendants are still there in many cases. So he has started to do some of this work, and other archaeologists as well of GPR. They've also hired as many Black American archaeologists and forensic anthropologists to work on the project as possible. And right now there's no real conclusions or finish of the project to bring forward, but archaeology and GPR and a few other of our techniques are really playing an important social role. Now, the actual GPR machines can be sort of heavy duty and look like just a very nice lawnmower kind of thing. For this one, here's one out in somebody using it in a dry soil in the Middle East. And again, as long as it's not super salty, you're probably going to get a pretty good read. And in every case, when somebody's actually using it, you'll see that line. They've already mapped out that line, so you know exactly where to come back to too when you're done. Okay, well, my timing was pretty good on these. I'm always surprised for that. All right, you all. So other than maybe just a couple little things that I might use to prep on Thursday from chapter 3, mostly on Thursday, just going to go over dating techniques, mostly on chapter 4. Remember, again, the examples of what we were learning about for these techniques are posted in Canvas. The visual activity for this unit is there, and you have all week to finish it, but it's a really quick, do this short read and write down some things that have to do with excavation and relative dating that go along with what we're learning right now. The quiz for this unit's going to open up in a couple days. It'll be the same as the other one. You have 3 tries to go through it, and the questions are going to relate to chapter 3. You're going to see questions there for chapter 3. And we'll be zooming towards finishing this up. So thank you again. If you didn't sign into chat, please do that. Otherwise, I will be working on taking a look